My name is Sergey. In this talk, I would like to introduce you to Open Data Fabric protocol and its use case in research data management. Open Data Fabric is our attempt to holistically address the problems of modern data management systems. It's an open source and free project. We've been working on it for over 2.5 years. Let's start by looking at a set of core problems we want to solve and deriving the requirements towards the system. Our society runs on information flows. Some of them are more structured than the others, but in all of them, information spreads around, is being transformed, enriched, sometimes unfortunately distorted, but overall it's a complex graph. In these flows, however, humans are often involved in every step of the way, taking data that comes as an input, transforming it, and exposing it as an output for the next stages. Because of the human involvement, all of this process requires constant coordination. And as a result, these flows might take weeks or even months to complete. The latency is so big that by the time data reaches decision makers, it's often already outdated. One example of such information flow are the daily COVID-19 aggregate numbers that you're constantly getting in the news these days. However, even for developed countries, it took us months to build up these information flows and make them reliable. In May in UK, they were still using phone, pen and paper to tally up the COVID-19 test counts across the labs. And government later admitted that there was a significant amount of double counting going on, and all those numbers should be considered completely unreliable and not used for research. In October, they switched to a shared Excel file to tally up the numbers, and when this file overflowed, it caused them to lose 16,000 test results, and this situation was unnoticed for over a week. So the failure of data infrastructure is considered as one of the main reasons for our poor pandemic response. One interesting thing about the information flow is once they're created, they typically stay active for very long periods of time. So think weather data and financial markets data. Those flows existed for hundreds of years and they definitely evolved over time, but they're still flowing and going to continue to flow. Research data management platforms, however, I kind of focused on this idea of a data set that is a snapshot, a bit of data that is completely frozen in time, which makes sense for the archival purposes and preserving the history. But the thing is that RDMs also play the key role in the collaboration around data. But collaboration requires something more fluid, more dynamic. So there's this inherent conflict between the static needs of archival and dynamic needs of collaboration. And the simple answer to this is that we need both. We need an archive to preserve a history, and we need a pipeline to collaborate on enriching and transforming data. Data in the system must flow with minimal latency. This means that we need to somehow remove human from the loop. And these pipelines need to be able to evolve so that any dataset could change over time without resulting in the destruction of the pipeline. A big part of collaboration is being able to reuse someone else's results. But currently, over 80% of data scientists' time is being spent on data search and preparation. So clearly there's something wrong going on with that part. Going back to COVID-19 example, imagine we have hundreds of hospitals publishing COVID-19 datasets, and as a researcher, you want to analyze this data. It will probably take you weeks or even months to unify all the formats and homogenize the data before you can process it. So wouldn't it be nice if some other researcher could do all this work for us and we all could reuse their results? So unfortunately, this doesn't work. Upon getting this data set, you will start wondering, how can I be sure that this data actually comes from those hospitals? Can I be sure that it was processed correctly and no malicious information was intentionally added into it? All of the research currently kind of operates on a good faith basis. But if you were actually to verify that the data is truthful, it will take you a comparable amount of time as redoing this entire work from scratch. So collaboration is clearly broken. And my example about malicious data is not even a hypothetical one. Last year, probably the second biggest medical news after COVID was the Surgisphere scandal, where big research was published that turned out to be based on completely fake medical data and derailed a lot of drug research worldwide. So many people are now talking about changing our defaults from believing that all the research is done in good faith to believing that research is not trustworthy until it's proven so. If we compare data to software, there is little to no reuse happening in data. This means that forward progress is constantly being lost. As we improve upon data, we cannot share these improvements without running into the trust issues. In software, meanwhile, the reuse and collaboration are flourishing, and all of this is thanks to verifiable trust enabled by the version control systems, giving us the ability to tell exactly where every single contribution came from associated to the person, make sure that it's not malicious. So verifiable trust in data would look like knowing exactly where every dataset came from, knowing its entire lineage, knowing exactly how every data cell was produced, knowing all the transformation that went into getting the resulting value, and ensuring, of course, that the data corresponds to these transformations, that it was not tampered. And ideally, we would like this entire process to take seconds, not weeks or months. Another big aspect of collaboration is reproducibility. It's a cornerstone of the scientific method, but 90% of scientists currently believe that there is a reproducibility crisis going on. A lot of them cannot repeat the projects of others, and most of the times they cannot even repeat their own projects a few months later. A lot of focus currently is being put on reproducibility of models and analysis. So using version control for the code, making sure that you have reproducible environments using tools like Docker and pinning all of the dependencies. But the problem here is a lot of the input data is non-reproducible as well. Majority of publishers currently publish data destructively. So once a day, they might publish a new version of a dataset with some additions or slight modifications to it, reflecting the current state of data. But at the same time, they're overwriting all of the history. This means that data scientists, to preserve reproducibility, have to resort to tools like data snapshots and versioning, putting the data as they saw it at the time aside, assigning an identifier to it, and reusing it since then. The problem, as we saw as during discussion around reuse, is that this data becomes completely disassociated from its source. It's now impossible to tell that this data actually come from this publisher. On top of that, it's pretty wasteful. If you have thousands of researchers making data science projects around one big data set, you will have thousands nearly identical copies of this data set. So naturally, this doesn't really work for data that is fast moving. So our requirements here is just to recognize that the data is our modern day history book and we should treat it as such. We want an ability to freeze any data set in time, so get the stable reference to it, but at the same time have minimum redundant copies of it. And since we're freezing something in time, it's really important to also account for the retractions and corrections that might come further. You don't want to freeze the data science project in time if there are some important mistakes in it. You at least want to be able to see those mistakes as they are further discovered. A lot of these problems could be solved by centralization, but we want to recognize that there will never be a world data warehouse because centralized solutions require a lot of coordination and often slow down the innovation process. It also introduces data ownership issues, right? You don't want to give out your data for someone else to store it. So there's a consensus that the future of data is decentralized. Everyone needs to be able to own their own data. But we also want for data to appear in this single place, so it's easily findable and easily usable. But we want to extend this federation requirements to include not only storage, but processing as well. We want these data pipelines of the future to be able to span across multiple organizations. So I really wish that from this beginning we understood these problems as clearly as I explained them now, but it took us over 2 years to arrive at the solution, which is Open Data Fabric. ODF is a protocol for reliable data exchange and transformation. It's a document that lives in the GitHub that basically specifies the world's first decentralized data warehouse. So you can think of it as a weird mix of Git, blockchain, and Kubernetes, but for data. A key aspect of ODF is this clear separation between source and derivative data. Source data is something generated by some external system or as a result of observations. So you can think of me recording weather data outside of my window as a type of source data, because if this data is lost, it cannot be reconstructed from anything. So publishers have full responsibility over veracity of the source data because nobody else can prove it. So it fully relies on the reputation of the publisher. Derivative data, on the other hand, is data generated by transforming some other data. For example, aggregating, making summaries, and machine learning models can also be thought as a type of derivative data. It can be reconstructed if all of the transformations are deterministic. In this case, veracity depends on the veracity of the inputs, of course, and the audit of all the transformations to make sure that they're done in good faith. This is a conceptual view of ODF. It's a complex graph in which source data, captured in the root datasets, as we call them, travels in near real time through multiple transformation steps that create the derivative data, and gets into the hands of decision makers, automation, machine learning experts, etc. People in the ODF are effectively removed from the loop. They are configuring the system by the means of data flow queries, but they're not actively participating in moving data around, ensuring this minimal latency of the system. A dataset in ODF is a ledger, a potentially infinite stream of events or observations. It only grows over time, so all of the data that made its way in is completely immutable, doesn't change over time. This means that giving out stable references like URLs or DOIs that point to the exact version of the data that you used for your project is very simple. It's just a tuple of dataset ID and a position in a ledger that you're considering. This means that if you have a dataset with billions of events, you can give out a billion of DOIs or URLs, stable references, at no cost. There is no snapshotting, there is no versioning, there is no duplication. At the same time, the validity of this data can be easily confirmed with a publisher by taking a stable reference and hashing the data that you have. If the hashes on your and the publisher's sides match, that means that you have a valid data. This is how a typical root and derivative datasets look in a system. A root dataset here, we're pulling data from an external source, in this case, Vancouver Open Data Portal, and we're pulling text property reports as just a CSV file. We instruct the system to parse it and merge it in with the existing data as a ledger. For the derivative dataset, we're specifying the inputs, which datasets we're going to be using to derive the data, and we're specifying SQL query in this case of how the data needs to be transformed. So a big part of the solution is realization that batch processing is actually unfit for purpose. Probably 99.9% of the data processing these days is in form of batch, but this method, however, is completely ignoring all the temporal problems of data. So think of late arrivals or out of order arrivals, backfills and corrections. If you have data sets that are constantly updating, you will get into the problem of matching the cadences. If one data set is updated more frequently than the other, they will never get into this consistent state for you to join them meaningfully. So this is where batch fails us, and it becomes extremely error prone and non-deterministic to write the batch transformations. And even if you were write a transformation that is correct, it will take you thousands and thousands lines of code, which completely destroys our property of being able to audit the transformations, because there's just no use for you to audit a 1,000-line of code transform. So this is where we switched to a new way of transforming data, which is streaming transformations and streaming SQL. The whole idea is that you write a query once and you run it forever, and it handles all the complexity under the hood. It's very familiar to anyone who used SQL because it's nearly identical to the batch SQL, but at the same time, all of the queries are very easy to audit. It has minimal latency and determinism, and it handles corner cases like corrections and retractions. In Open Data Fabric, raw data never travels alone. It's always accompanied by metadata. And this metadata acts as a digital passport for the data, specifying where exactly every single piece of information actually came from, how it was achieved. It's also a blockchain-like ledger that is cryptographically linked to the data. Most common metadata event is of course just adding data into the data set, but it can also reflect things like schema changes, like a column was added into the data set, and etc. This is a key enabler of efficient sharing and the evolution of data sets and reproducibility and verifiability. But on top of that, it can act as a platform, allowing us to codify a lot of the data workload things like governance, compliance, privacy, and audit. So it no longer becomes like a standard that you have to read and comply to. We can actually put all these requirements into the system itself. This is how dataset looks like on disk. It's a pretty simple structure. There is nothing proprietary about it. All of the raw data files are stored as Parquet files, columnar data format. And the rest of the structure is very similar to how Git stores your software code. So a series of metadata blocks and references to those blocks. And we also have checkpoints that capture the state of the streaming processing as it happens. One of the most interesting implications I want to highlight is the one around data sharing. So for the source data, of course, because it's not reproducible, we still want to use durable and highly available storage, just like all of the RDMs are using now. For derivative data, however, we're free to use any cheap, unreliable, or even no storage at all, because derivative data is essentially a form of caching, right? You can, because the transformations are deterministic, you can fully reconstruct it by just having the source data and the metadata together. So this means that when you have thousands of data sets and millions of researchers doing small projects around these data sets, instead of storing petabytes of different snapshots for the data that is rarely used, you can replace all of them with just megabytes of metadata and reconstruct the results on demand, whether it's on a server or directly on the user's computer. We can always rely on metadata to confirm that the data that is reconstructed matches that it was originally. Kamu is the name of the tool that implements ODF protocol. It's a single binary app that you can download and already give it a try, and it allows you to build sophisticated data pipelines directly in the comfort of your laptop. It's very Git-like, so here you can see me adding a data set from a YAML file, pulling the data from the source to ingest it into the system, and you can inspect the list of the data sets, so it allows you to manage dozens of data sets simultaneously and inspect all of the commits that the data sets are composed out of. It also comes with a very convenient SQL shell that you can use SQL in to explore the data sets, or you can even launch a Jupyter notebook and start exploring the data there, being able to install all of the necessary dependencies that you need to visualize data. So our long-term vision for the Open Data Fabric and our value proposition for our DM platforms is to start moving together towards this new generation infrastructure for structured data, one that combines archival and collaboration without any compromises, where real-time data can flow that is 100% reproducible and verifiably trustworthy. And the entire solution is more space efficient than currently by avoiding the pitfalls of versioning and snapshotting. We want to invisibly guide all of the users towards best data management practices. So this means taking the standards and all of the compliance routines that currently exist in form of workflows and codifying them, enforcing them in the tooling itself. Having long-living datasets also means that there will be fewer datasets in general to deal with. Means that it will be easier to start systematizing the knowledge that we're currently producing. And these tasks, including harmonization and linking, can all be crowdsourced. Just how we collaborate on software, we could collaborate on making data better together. Such system would also create new incentives for publishers. So instead of having just a download counter as on current platforms, or waiting for DOI of your dataset to show up in some publication, you would in real time see all the pipelines that are being built on top of your dataset. So publishers would be adequately rewarded for all the data that they're contributing towards the society. These pipelines would also make data readily available in minutes to decision makers, automation, machine learning, and smart contracts. And I didn't mention the privacy aspect of all of this at all, because privacy is such a big topic. But all of the developers of the major research data platforms we talk to, they agree that there's a lot to be done on the privacy aspect. And they all see that privacy is no longer a binary thing. Your data is no longer strictly open or strictly private. It's a spectrum. And on the spectrum come these solutions like differential privacy, federated learning, etc. But they're all technologically complex. So they require some infrastructure to be in place for us to start implementing them. Otherwise, every data platform will probably implement their own solutions, which all of them are not going to be interoperable. So we need some sort of lowest common denominator to agree on how data looks like and how data needs to be exchanged, and then start building the privacy framework on top of that. So I hope this all was useful and interesting, and definitely check out Kamu CLI and check out our examples, and let us know if you have any questions. We're very interested and open to collaborating with you. Thanks.